Okay, the diagram shows an electron undergoing uniform circular motion. So uniform circular motion means it's moving around at a constant speed in a circle. The radius of the orbit is 1.5 nanometers. Calculate the distance moved by the electron when it goes through an angular displacement of 40 degrees. So angular displacement is the angle is turned through. Okay, it's represented by theta here. Okay, it's normally actually measured in radians. So here we've got in degrees, so we're going to turn that into radians soon. We're trying to calculate the distance traveled, or the arc length in this case, S there. Okay, that's linked by this equation, S, which is the arc length in meters, or the distance in this case, and R is the radius of the orbit or rotation measured in meters, and then theta, which is angular displacement, again in radians. So let's turn the 40 degrees into radians, so 40 degrees divided by 360 and then times by the equivalent of 360 in radians, which is 2 pi, and that gives us 0.70 radians. And then we can do the displacement here, or sorry, the distance moved equals the radius, which I've turned into meters from nanometers, times the angle, and that gives us the distance moved, which is 1 times 10 to the power minus 9 meters. The geostationary satellites do uniform circular motion around the Earth with a time period of 24 hours. So time period means the time it takes for one orbit, one cycle, one revolution. You would have come across this term in the waves topic, where it stood for the time it takes for one complete wave. Here it just means the time it takes for one complete cycle of anything really. Okay, the radius of the orbit is given in kilometers. We're asked to calculate the speed of the satellite. So speed is distance divided by time. So in this S here, you could use arc length, which is r theta, but we're given the time period, which is capital T. So in one time period, it's going to do one whole rotation. So we know it's going to travel the circumference of this circle. The circumference is 2 pi r, so we can put that instead of r theta here. So we put 2 pi r here, we get this equation, very important equation. The speed equals 2 pi r, which is circumference, divided by the time period, the time it takes to do that. So in this case, 2 times pi, and I've turned the radius from meters to kilometers, so from kilometers to meters, divided by time. That's 24 hours, so I'm going to turn that into 60 minutes times by 60 seconds, and that gives me a speed of 3070 meters per second. Okay, a gear in a car is rotating at 300 revolutions per second. So 300 revolutions per second, that's like saying how many rotations per unit time, or number of oscillations per unit time. It's basically the frequency. Okay, so in the waves topic, you would have seen that as the number of waves per unit time. Here we're just doing number of rotations or orbits per unit time. So that's frequency is 300 hertz, because hertz is the number of waves or oscillations per second. Okay, so the diameter of the disk is given, and we'll calculate the speed on the edge of the disk. So we just saw the equation for speed, which is the circumference divided by time period. Now we also know the time period is 1 over frequency. So if we put that in, we get this equation here. And I'm just going to put the numbers in. Here I've got 2 pi r. I've turned from centimeters into meters. I've divided the diameter by 2 as well. And then I've times by the frequency to get my speed of 113 meters per second.